function calling for LLMs. My name is Jim Dowling. I'm CEO and co-founder of Hopsworks. And let's get cracking. So I hope you've been enjoying the conference so far, virtual event. Like I mentioned, I'm from Hopsworks and my name is Jim Dowling. And if you're interested in following along, this is a practical. I'm going to show you some practical code here. What I recommend you doing is taking note of the URL at the bottom. That's the URL to these slides. There's links later in the slides for accessing the code and instructions for this tutorial I'm going to walk through. It's all open source. It's all running on free infrastructure. It will run on Hopsworks, where you can create a free account with 35 gigabytes of free storage. It will also use Colab. We're going to use Colab because we need a free GPU to work with our LLMs. So let's get cracking. The context in which function calling is important for LLMs, I think, is in the context of what we call compound AI systems. So AI systems that do more than just a single call to a model, but do multiple calls to multiple models. So we'll see today that function calling is actually two calls you'll make to LLMs. The first call will be to ask the question, and it will respond with a function that it thinks that the model your application should call. And the results of that function will then pass back with our query as part of the prompt to the model again, where it will reason about the new data that's been added and give you your answer. So in fact, function calling is a very bad name for this paradigm because it's not like a LangChain where it's going to call multiple functions in a chain. It's really just a large language model that will return structured output as JSON. So we're going to take the JSON that was returned as an output, which will actually be a function with the parameters filled in. And with that JSON, we can then call the function. So that's the context. It's compound AI systems. There's a good paper about this by the people at Berkeley AI Research Lab. Now, the other context in which function calling exists is in what can you do to make large language models work better with your data and with data that has become available since the cutoff time in which the model was trained. So we all know that large language models have a model of the world through language. So through modeling language and the knowledge that's implicit in language, we get a fantastic model of the world. But large language models do not have a model of your private data. And that's often why we use fine tuning to take our private data, and we can then teach the model. You can actually train the model new information. It's hard to update old information, but you can actually add new information to pre-trained models with fine tuning. But then we also have this area of RAG, retrieval augmented generation, where we take external data, data that's become available since the cutoff time at which the model was trained, but also context information and historical information that maybe is not public. So it wasn't available for the large language model when it was scraping the internet for all the data to be trained with. Now, combining both of those two is a really powerful paradigm. You can often replace, for example, a very expensive OpenAI model with an open source foundation model that you fine tune without a significant loss in performance if you fine tune. RAG we need all the time if we want to incorporate any real-time data or external data or private data that wasn't available to the large language model that we're not going to incorporate with fine tuning. Now, where function calling comes into this is if we look at function calling is in this kind of larger space of if we have retrieval augmented generation, many people associate it with vector databases. So vector databases enable us to take the query string that the user enters into their large language model, find related chunks of text that have been encoded and stored in this vector index, and then using similarity search, we'll find the closest matching text chunks and we'll add them to your prompt. And that's a probabilistic method for finding related information to your query that may help the model reason about the answer it should give. And that's useful. We're going to talk specifically about function calling today. I'm going to walk through an example. And the example, I'll introduce it in a second, is forecasting air quality. So when you want to forecast air quality, it doesn't really help to have a vector database in this case. What we have is we have a model that we're going to train to predict air quality. And we'll also have some historical air quality data stored in a tabular data platform. So in this case, it's going to be a feature store, but you could think of it in general as being any database or data warehouse. So what we're going to do is we're going to take the user query, convert it into a function which will either retrieve a prediction for air quality or get historical air quality from the tabular data, and then we'll incorporate that information in our prompt, and then we'll ask the question. So let's see what I mean to be a little bit more specific. I'm currently close to this particular air quality sensor here in Manhattan at Hell's Kitchen. So I've actually trained a model to predict air quality at this particular location. I'll go a little bit through how I predicted that model later on, but this is just to give you an idea. We can see that the air quality varies a bit here. This is a website where there are tens of thousands of air quality sensors available globally, and you can get real-time information about the air quality at a given location with an API key. So you register for an API key here, and then your program can get air quality. And you can see we've got a lot of historical air quality going back to 2019 here. And you can just download that as a CSV file. So this is a quite easy model to train. We download the historical CSV data. We have a pipeline which will pull all of the measurements that are going to happen in the future. We'll pull them every day. And we're also going to have to predict the air quality. And I'll talk later about how we predict it with weather. We're going to predict it with wind direction, wind strength, but also temperature and precipitation. So they're the only 4 features we'll use. And there is, you can see here, a prediction for air quality already. Now, I bought one of these sensors and installed it in my house, and I can tell you that this doesn't work, right? So this is just some sort of, I think it might be an aggregate over New York or over a larger area. But the problem with air quality is that it's very localized. So you can see here, just up here in slightly east of Central Park, we can see the air quality is not so good, but here at Hell's Kitchen, it's quite good. So you can see it's very, very localized, and over here it's quite unhealthy. So that's kind of the importance of this problem of air quality forecasting, is that if you were to repeat this tutorial and do it in where you live or a location that's important to you, you could have something like the following. You could have this dashboard that you make publicly available. I'm using GitHub to make this publicly available. It's predicting the air quality here. And you can see the air quality looks okay for the next few days. But what I want to do with large language models here is sprinkle some magic dust over this air quality prediction system. You know, I can go and apply for a job and say, hey, look, I built this air quality prediction system. And you can impress someone that you built an end-to-end AI system that takes new data, keeps making predictions, and has a useful service with a graphical user interface. But wouldn't it be even cooler if I could ask questions of the model? So if I can ask questions like, what was the air quality like last week? And it will give me answers. The answers you can see here is the PMI, the PM particulate measure 2.5. I can ask it also historical data, but I can also ask it future data. So we'll have a look at, let's run one of these here while we're here. So what will the air quality be like the day after tomorrow? I'm running it quickly, by the way, because I'm using a free GPU in Google Colab. And if you're familiar with Google Colab, they take your GPU off you very quickly. So I just allocated this 30 minutes ago. And if you leave it running too long, it'll get pulled off you. Now you can see that it takes a bit of time because the model I'm using is a fine-tuned model based on Mistral 7 billion. The model is called OpenHermes 2. It's been fine-tuned to return JSON, structured JSON object. Okay, so it says, based on air quality measurements, the day after tomorrow is expected to be 140, and this falls into unhealthy. So that's not great, but you know, what was really nice here is we have a model now that can basically, and we can ask it other questions like in a particular date, or we can ask it, you know, a future day of the week as well. So it's able to interpret human natural language. And this is the magic dust that I'm sprinkling on top of my air quality example. Sorry, the wrong tab. Let's go back and look at the slides. Okay, for those of you who joined late, you can take this link. So quickly take a photo. These are the slides, and I'm going to go through the example. And you can access these slides, and there'll be links to the source code that you can follow along with. Okay, so let's get into it, and we'll look at function calling. So we went through function calling here. In Hopsworks, specifically the support that we have for function calling, but also for vector index. There is a vector index as part of the Hopsworks feature store now, is that we store tabular data in these feature groups, including embeddings. I'm not going to go through embeddings today. This is RAG without a feature store. And we're going to do function calling on the feature group. We'll also do function calling on the model, which isn't shown here. But if you want to do fine tuning, we can do fine tuning as well in Hopsworks from feature pipelines, creating instruction data sets, fine tune those, and make those models then available to your inference pipelines. This is typically how we structure the applications. I'll get into that in a little bit. So what does it mean to do RAG without a vector database? So many of the examples that you'll be familiar with for RAG is basically look something like the following. We have a user, they issue a prompt, there is an external data source, it's assumed often to be a vector database, and we'll pass it the prompt, so the user query that was entered, and it will retrieve the chunks of text that have been inserted into this vector database that are the most similar. So there's many parameters you can use to tune what ones to find. So you can have, you can obviously hyperparameter is the chunk size. Is it going to be page, or is it going to be, if we're doing PDFs, for example, is it going to be per page or paragraph or sentence? But then we have other ones like temperature and distance, the number of elements that you can return. It depends obviously on the context window size of your large language model. So there's a few things you can play around with here. You can even do things like re-ranking. But honestly, all of this is really just, they're probabilistic answers. If you're going to build a production system here that's going to return data to you, often for the example I'm giving here, that you can't really work that into a vector database. So, just to put that in a slightly different, let's look at this in a slightly different manner. Your question comes in, we go to the vector database, we add the similar prompts that we get back to our, what we call the preamble, or it comes before the question in our prompt, our context, and then we go to our large language model. And the obvious question here is the prompt, this input prompt or query, the only available data you can use for RAG? And the answer to that question is a resounding no. And here's a very simple example of where we can include additional information beyond the input prompt or query. So here we have an LLM application here now. It's no longer just a random client. We have an application that you've built. And in that application, you have authenticated yourself. So there is a user ID. The user's logged in. There's either a user ID and possibly also a session ID available. And with that information, I can go to an external database, an external data lake or data warehouse or feature store, and I can retrieve a lot of information related to the user. So for example, wouldn't it be great if I could say, well, what has this user done in my system in the last week? Well, if I have the user ID and I know the tables where that data is, and there's a timestamp in the column with those tables, I can have a function which will make the SQL query to retrieve all of the data in the last week for this user ID. And that's what we're going to do in the air quality example in a minute. And the results of that query that we issue on the external database, we include in the prompt as the preamble. And then we pass that on to our LLM. Now, there are alternatives to user ID you can use. There's also a booking reference number, an order ID, a session ID. You don't have to build an LLM application where users are authenticated. If I have a retail application, maybe the user just enters their booking ID, but that booking ID, again, can be used to retrieve other information, such as the user ID, what the user has purchased recently, and so on. Now, if we want to add the model in here and include function calling specifically, what our LLM chatbot will look like is the following. Firstly, the user will enter their query, this question, and we have a prompt template for function calling that we'll look at later on. And what we're going to do is we're going to then fill in the user question and the available functions. There's going to be a small number of functions that we're going to say, these are the functions that you can call. And in fact, the functions that we'll have available will be, firstly, one will go to the tabular data and say, give me the historical air quality for this specific date. Give me the historical air quality for this range of dates. And then we'll have another function, a third function will be, give me the future air quality for this date, or give me the future air quality for this range of dates. There's only 4 functions in total. And what the LLM will do is figure out, based on the question, should I call one of these functions? And if I do call one of the functions, I need to fill in the parameters to those functions. So I need to fill in the dates. So for example, if I say, what will the air quality be like the day after tomorrow? The prompt template includes today's date, and it's able to, the LLM is able to reason and figure out, okay, today is whatever the 9th of May. So the 11th of May is the date that's referenced here. So it'll fill in that as the parameter to the function. And then we'll be able to make a call on the model saying, can I retrieve the predicted air quality on the 11th of May? The results of that call, the predicted air quality on the 8th of May, 9th or 11th of May, sorry, will be included in the second LLM call that we're going to make, which will say, hey, the model predicts that the air quality on the 11th of May will be X. And then we have the question, what will the air quality be like the day after tomorrow? Again, today's date will be here. So the LLM will be able to give back a good response here. This is the basic thing we're going to build and have a look at. But let's have a look at just before we do that and say, well, we have function calling and we have vector databases or vector indexes. Can we combine them? This is another example that we have in our tutorials if you want to look at it. Basically, we have a very nice example where we take private PDF documents and we index them. We index them in Hopsworks feature store in the vector index in feature groups. And then a user is able to ask a question. The question will say something like, tell me about X in the documents. We'll get similar text snippets or chunks based on the question here. And then we'll add those to the prompt and we'll give you the answer. And this is great. You can ask questions about private data that the LLM doesn't know anything about, and it'll give you good answers. And obviously having a large context window helps, having good chunking policy helps. But in general, this is a very practical system you can build. However, can we make it any better with function calling? And the answer is yes. We can improve this because this example has no personalization. So if, for example, I want to know about, let's say, medical advice, it wouldn't know anything about who I am and my conditions, my personal conditions. So the system might be able to give generic medical advice, but if it knew about my particular information, it might be able to give personalized medical advice to me. So we can do that and add that with function calling to this type of RAG application. Here we have now a client. We can see the user's logged in. So we've got the user authenticated, and the user said, tell me about X since last week, whatever X is. Function calling can look up information related to me and say, well, X is valid for you, Jim, but maybe not for other people. And then it adds that information to the prompt in addition to what we had earlier with the vector index. We can get back the same chunks of data. Now we can get a personalized answer based on the documents and the user's personal information. So we can combine RAG and vector and function calling to make personalized RAG, which is great. So let's get into the example that we're going to look at. This is the air quality forecasting example. Now I will build this based on an architecture we call feature training inference pipelines, or FTI pipelines. It's a really great way to structure or modularize your AI systems so that they're easier to develop. So what we end up with is an AI system will look like the following. We'll have raw data in here and predictions coming out at the right, but we won't have one giant program. We're going to modularize it into a feature pipeline, which takes raw data in, outputs features and labels, a training pipeline, which takes features and labels and outputs a trained model, and then an inference pipeline, which take our trained model and features and output predictions. So what we do is we connect those pipelines together with a Hopsworks feature store. The feature store is a platform for managing your data for AI throughout the life cycle of feature engineering, training, and inference. And we'd also need a model registry to store our models in. So Hopsworks includes that. Now let's look at this particular architecture, the feature training inference pipelines with the shared data layer here in terms of large language models. This is one example I mentioned. We have these personalized PDF querying with RAG. So it's a unified architecture for fine-tuning and RAG. In Hopsworks, it looks as follows. In feature pipeline, we can take documents like markdown documents or PDF documents, chunk them, compute embeddings, and then write them to our feature store, to the vector index in there, so the approximate nearest neighbor index. We can also create instruction data sets in here as well, using a trainer model like GPT-4. And those instruction trained data sets will be used to fine-tune models in a training pipeline. And then we save those models to a model registry. We'll see later on that Hopsworks has a file system which enables you to easily deal with these huge models that are tens or even hundreds of gigabytes in size. Not all model registries are designed to handle that scale. But then finally, in our inference pipeline, we can combine our fine-tuned model with the RAG capabilities and function calling that we have from earlier. So this architecture, feature training inference pipelines, is a unified architecture. It works for LLMs, as we can see here, but it also works for batch and real-time systems. Now, if we dig into what's in the feature store, there's effectively two abstractions that we have to deal with. One is that when we write from our feature pipelines, we write to tables called feature groups, and they can have vector indexes in them. And then we have a feature view, which is the selection of features from the different feature groups. So it's just metadata. That's the interface to our model, and that's going to be used to create training data, but also to create snapshots of batch inference data or online inference data, so pre-computed features that our models may use. So they're the two abstractions, feature groups and feature views. That's all you really need to know in Hopsworks to kind of work with the platform. So a little final note on Hopsworks itself. It is this data layer for AI. And you write your ML pipelines and AI applications in whatever technology you like to use. If you're on premise, you can use Hopsworks itself. If you're in the cloud, you may use Spark or Flink or Pandas or Polars on any of those platforms that run those pipelines, Airflow and so on. But then Hopsworks is this data layer, the shared data layer here. I mentioned already the feature store. There is also a model registry I mentioned, but there's also support for model serving in terms of K-serve. And then we provide APIs for these three different ML pipelines, the feature, training, and inference pipelines. And beneath it, we're a data company at heart. So we have our file system, which is built on top of S3. The data is ultimately stored in S3, HopsFS. And then we also have our own database, RonDB, which is a fork of MySQL cluster. And currently our vector index is in OpenSearch. And we can store prompts as well back in our online database, RonDB. But let's briefly look at the file system. So one of the challenges when you work with large language models in the cloud is the performance of reading and writing from S3. Now, NVMe disks, which are local disks which are attached to your PCI bus, are very high performance at the moment. So you can buy 13 gigabyte per second NVMe disks that you can use in your own data center. Unfortunately, in the cloud, we're looking at around 2 gigabytes at the moment, but we expect that they'll have the newer NVMes there soon as well. But with the 13 gigabyte NVMe drives, we can load Llama 2, which is 260 gigabytes, into memory in 20 seconds. It's going to take you about 1,000 seconds nearly from S3. So that makes a huge difference in terms of your iteration speed when you're working with LLMs. You can also, of course, have a local NVMe disk and copy your data in and out of it, but in a shared enterprise environment where people are storing their data in this shared infrastructure, so a shared file system, ultimately on HopsFS, the data will reside in S3, but it's tiered storage over S3. So the latest data will be stored in the NVMe disks, and then the historical data in S3. Okay, let's get into we've got a few minutes left to do our demo. The code is publicly available here. It's actually part of a book I'm writing for O'Reilly. It's the third chapter in the book. And the problem itself is just to build this weather forecasting, air quality forecasting, machine learning powered service. And then we're going to use LLMs to interact with it. It uses a couple of APIs. I showed you already the air quality data we can get from this AQCICN website. And then the weather data we can get from OpenMeteo. They give you a free API for getting weather. So what we do is we download the weather data into a table. It has a city name, a date. We have the 4 features that I mentioned that we'll use to predict air quality. So the wind speed, direction, temperature, and precipitation. And we can see that data. Let's have a look at the data when it gets written into Hopsworks, what it looks like. So, whoops, I'm kind of double clicking on stuff here. Let's see, go there. Okay, so this is Hopsworks here. So, so I ran these programs before. It's free to create an account here, as I mentioned. This is the hosted version, the serverless version. You can, of course, install in your own cluster or in the cloud. There's a managed version in the cloud. But I ran a couple of feature pipelines, which are in the repo, and it read the weather data for my location. And you can see here that these are my features here. I mentioned we've got precipitation, wind direction, city, date. We can quickly look at that data if we're interested in seeing what it looks like. Here you can see it shows us some data. There's a primary key here, which is the city name. And then we have an event time column, which is the data which the measurement is made. You can have a look at the activity on that table over time. So we start off and ingested 2,000 rows, and then we ran the pipeline to download the weather forecast for the next 10 days, and so on. We can also look at statistics for the data. You can see it gives us descriptive statistics for our numerical features. So the temperature was max 30 degrees and minimum was -11 this time range that I took the data. Okay, and we did the same for air quality. So in air quality, we have a little bit less information. We have the country, city, the street, the URL. This is our URL to the data here. That's the URL for getting the real-time data from there. And then the date. So the primary key here is the country and street name. And then the event time, in this case, is the date at which you made the measurement. And we can have a quick look at the data here. We can see here you've got PM2.5 is our particulate measure 2.5. That's the actual air quality. And again, we can look at statistics over these features. So PM2.5 max was 138 and min was 0.4 in the time range of data that I had. And you can see I got some historical data here, again, 2,000 rows, and that's great. So that's our data that we worked with to train our model. This is the air quality data, and we use the column, the PM2.5 column, we're using as our label in a supervised machine learning model. So the way we wrote this code in Hopsworks is basically the weather data frame we get by reading from this Open Meteo API. It'll download the data into a data frame. We create the feature group, we specify the primary key column and the event time, we give it a description, and then we insert the data frame, and that's it. We can also add data validation rules as well, which I did in the code if you want to look at it, using great expectations to make sure that the data inserted follows whatever those data validation rules are. So for example, there's a data validation rule saying that the PM2.5 value can never be negative. Which is it shouldn't be negative, and it shouldn't be over 1,000 either. So it's a very simple rule to ensure that there's no anomalous data ending up in your feature groups. So this is the air quality. We do the same thing. We use the API to get the data, the live predictions from the real-time API, but we also download the CSV file. So we have a notebook to read the CSV file, create the feature group, and backfill our feature group. Now, once we have written our data to these two different feature groups, Hopsworks includes this feature view that I mentioned earlier as a way in which to select the features that we want to use to train our model, but also perform inference with. So what we do is we get a reference to our air quality feature group and our weather feature group, and we select the features we want to include from both of those different feature groups. And here I'm selecting PM2.5 from the air quality feature group, and I'm joining it with all of the features in the weather feature group. Now, I don't specify the column in which I'm joining them together. The query engine is smart enough to realize that the city name is part of the primary key of both feature groups, so it can figure out that should be the key to join on. But you can, of course, override that and explicitly specify what column to join on. With the selected features, I can now create this feature view, give it a name, say what the label is, because the feature groups don't have labels. Labels only exist when we want to actually create a model. We can say this is the label or target column or columns that we're trying to predict. And because in some models, something that's a label in one column, it may be, a column in one model may be a label, but that column in a different model may be a feature. So we only decide at this point with the feature view which columns will be the labels. Okay, so once we have this feature view created, what we can do with it is that we can create training data from it, and we can train a model with it. So firstly, there's a really nice scikit-learn style API you can use. You can see fv.trainTestSplit. I think there is also, of course, a time-based split where you can specify time ranges. I think I used that in the code, but it's a lot more code because I specified the start time, end time for the training sets and test sets. Here I'm just splitting it into training and test sets. So we've got X is our features in the training set, and X in the features in the test set. Y are the labels in the training set, and Y are the labels in the test set. And now I've got my data frames with my data. Let's go back here, sorry. I'm going to encode the categorical columns with one-hot encoder using scikit-learn, and I'm going to use XGBoost as my model. So I just call fit on my training set, features and labels, save the model as JSON, and then I create the model and I save it to Hopsworks. So in Hopsworks, In the new version that's coming out, you basically specify that the feature view that was used to create the model was this one, and then it will extract the interface to the model. So the input scheme and output scheme of the model will be taken from the feature view because that stores that particular schema. That's an optimization we have in the upcoming next release of Hopsworks. So finally, I save my model to Hopsworks, and let's look and see what happens at that point. You can see that we created this feature view here, the air quality feature view with all of our columns. These are our features and labels. And then the model itself got saved in here. So we've got this model here, and we saved some evaluation images with it. So in the notebook, we saved this hindcast to see what the performance of our model was. It's pretty okay, not too bad. And then we can see the feature importance. So the temperature was actually the most important feature, surprisingly, for that model. So then we can make predictions. So we can actually then say, okay, let's use our feature view. This is a separate program, the batch inference program. We run it on a schedule, so it can run every day, get the batch of feature data, so the next week of weather data. And with that weather data, we can call predict. It'll predict then the air quality PM 2.5 values. So that's all that's happening here. We're downloading our model from the model registry. We make our predictions with the model of the PM2.5 measure, and then we can save those into an image, and that's what we do here. We basically save an image. Here we output we're basically saving this as an image, and then we're using something called a GitHub action. So the program here, this is the code in here. We can see it in the repo MLFS book. There's a GitHub action here, which we can look at. You'll need to uncomment this line if you want it to run every day. Otherwise, you can just run it from the user interface on demand. But basically what it does is we run the feature pipeline to generate to get the weather forecast for the next week. And then after we've done that, we read the weather forecast for the next week, and we use that then to make our predictions of air quality. And what it does is, in fact, it outputs or saves then these PNG files, which are the chart that we want to have here. And then we have this commit action, which will then publish that to this dashboard here. So everything kind of happens in the background, which is great. So then I mentioned that we add the LLM to interrogate this model that we've trained. So again, the code is in here and the instructions are in here. I can show you briefly the code. We can have a look at it in here. It's this one here, the function calling notebook. This is the one I showed you at the start. So you'll need to uncomment these lines to install the dependencies. You can see it's using some Hugging Face dependencies. And because I'm importing some modules, you'll have to uncomment this. It's going to basically Colab is not very good at using modules that aren't maybe registered with PyPy or something. So I have these modules defined in my code in here in this functions directory. So it's basically going and downloading them from GitHub, from the repo. It basically connects to Hopsworks. It gets a reference to my feature view, downloads my model, and then it downloads my LLM. And this step takes quite a while. It's about 35 gigabytes. But we don't use the full model because it wouldn't fit into memory on our T4 GPU. So what we're actually using is we're using a bits and bytes, you can see here, to quantize the model into 4 bits. So we're loading with 4-bit config, and then we'll fit in memory. It also caches the model in case, because sometimes, like I mentioned before, if you lose your GPU and you get it back, if the session is still active, you'll be able to load from disk then instead. Okay, so let's have a look at some of the details of this LLM model before we wrap up. Firstly, we need to have a prompt template. So we have 2 prompt templates that we include in the code. One is the actual question when you say, ask about the air quality. So here we say, okay, we start with saying you're one of the best air quality experts in the world. Don't show any calculations, just give them an answer, explain the reasoning for the answer and so on, give the data in here, and then add this context. Now this context that we add here, this is what the results we get back from our function calling. So the function calling is this particular prompt. This is the interesting one. So this prompt you should only use with a model that's been fine-tuned for function calling. And I mentioned already in the open source world, there's really 2 models that stand out. One is this Open Hermes. There's versions 1 and version 2, which are fine-tuned models of Mistral. There's now a new Open Hermes fine-tuned model on Llama 3. So Llama 3 actually has good support for function calling as well. And then the one of the best ones, I think Gemini and OpenAI both have good support for function calling as well. So GPT version 4 has good support for function calling. So in the code, actually, there's also, sorry, in the repository, there's also a Gradio standalone application which allows you to switch between OpenHermes and OpenAI. So you can try either of them and see what you think. So here's the way it works. You basically, this prompt is going to take our function and it's going to serialize it. It's going to take it and convert it into JSON. Now, this particular function, again, it's defined in the repo, but one of the important things with function calling is that we have a lot of metadata. So if we look at Hopsworks here for these, if we look at our columns here, so we've got PM25, we can have a description of every single feature or column in these tables. So we can extract these and put them in the function call so that there's a lot of information available there, including the description of the feature group itself. And that metadata is needed and used by the model to basically understand what the function should be doing and to be able to go from the user query to say, well, this is the correct function to call. There's a little bit, there's a spelling mistake here I can see, and didn't really seem to bother the model too much. It's a little bit specific, telling you how to return dates. And we want the answer to look to be returned in this particular format. So we're going to get it back inside this these set of Excel or XML tags. So once we get our, so let's have a look at the code then for what's happening internally. These are the functions that we have here. And as I mentioned, there is some metadata omitted in here. There are only the 4 functions to get the historical feature data from the feature groups, but also to get the future feature data from the models, based on either a point in time or a range of time, a date range. So if we dig in and look at the Hermes 2 code, what actually happened in there, the way it works is that firstly we take the user query and then get back the function calling prompt. So it's going to fill in the prompt with the information that we had there earlier with the functions. Now we need to make a call on that model. So we take our model and we get a tokenizer for it, and then we get the generated tokens. So this is our output here, and this generated tokens we decode into this completion, and with this completion we say this was the function to call. So extract the function call that I should call these functions and then run the first one. That was the one that we want to call. We invoke the function, but that function may also need parameters like the feature view, weather feature group, and the model, and we pass those as functions here as well. So the once that function is called, it will return its answer as data, and then we include that data in the context. We build up the context, and this context is used then for the final model call, which is this one here, which will say, this is the context, this is what I got back from my function call, this is the user query, here's today's date, and that's then the answer that we're going to get back. So that's pretty much it. If you want to learn some more, I'm writing a book for O'Reilly. The first 2 chapters are available for free. You can go to the Hopsworks website, you'll find it. The code for this air quality demo is available at this link here. And there's a link for the instructions for this tutorial actually earlier on. I kind of skipped over it here. It's this link here, tutorial instructions. It's a Google Doc. And you can reach out to us on we have a research paper upcoming if you're interested in the performance of the platform. We have some incredible numbers coming out showing how we 10x some of the most famous platforms out there in the space. But you can go to our Slack and register there to find out, ask questions, and get help if you want to get started on this. So that's it. And there is a link to the slides somebody put into the chat. Thanks, Faraz, for that. If there are any questions, you can ask in the chat for the moment. And I don't see any questions in here at the moment. I'm going to just stop sharing my screen. So if there aren't any questions, thank you for attending and enjoy the rest of the event. Thanks very much.